Hello again, this is Professor Scott Sampson, and today I'm going to do a little review of topics from Chapter 3 of the Discover AI online textbook. And more information. This is not a substitute for studying the chapter and the concepts that are listed in the chapter, but hopefully will help in your preparation study of this material. So, this chapter is about, loosely I call it the term tools, although unfortunately the term tools has taken another meaning in the context of AI, but I love tools. There's a lot of tools, and in class sometimes I'll do this exercise, name that tool. Do you know what these different tools are called? And there's a lot of different tools that we have that we use in, woodworking or home construction or yard maintenance or whatever like that. So, I'm not going to go through those now. This actually is the names of these tools that are here in this particular DeWalt toolkit. Every tool has a purpose, and the point of this is probably the most important thing to take from this chapter, is the fact that sometimes people use the same tool for everything and it doesn't work real well. So for example, sometimes people will use ChatGPT for, composition and editing and data analysis, things like that. And sometimes that's good and sometimes it's not. ChatGPT or the GPT models in and of themselves are actually pretty limited in what they can do. We really require tools to enable us to do more complex things and specialized types of tasks. And even ChatGPT or Gemini or any of the models, they tend to access tools these days, which means they have the ability to draw on other types of systems to solve the problems that we need to solve. All right, here's my example here. This is an older picture of a white-haired professor cutting down a tree with a chainsaw here. I don't know why he's cutting so close to the ground, because that's very hard on the chainsaw blades and can actually damage the blade if it hits rocks or soil or things like that. But anyway, a chainsaw is the tool for cutting down trees. You can try other tools, but it's not going to go real well. So the point is, specialized tools are necessary. Another key element or principle from this chapter is the fact that the large language model is not the system. Some people think of, like, for example, ChatGPT versus the GPT models. They consider them to be the same thing. They are not the same thing. GPT is the model. ChatGPT is the system that includes other elements besides just the large language model. So there's a diagram that sometimes I'll show here, and in this diagram we have over on the right an end user, and they put in their prompt. It goes through a user interface, it goes through an embedding model, it goes through a vector database, a data filter, there's an initial prompt. So this is a system like ChatGPT. There's the initial prompt, but then they optimize the prompt. You may have to call different types of APIs, application program interfaces, things such as SERP, search engine result page, or either other types of tools. That's where the tools are. These plugins, they used to call them plugins. It's a little bit of an old diagram here, because now we don't call them plugins as much. People tend to call them tools, and we have connectors to these tools. Sometimes they call them connectors. Sadly, OpenAI has recently decided to not call these connectors. They call them apps instead. An app is different than an API. And then they optimize this. They then send it to the large language model, and it might have some cache involved, and then it does some filtering, and then we have the output that goes back to the person. So it's interesting. At the bottom, we have the LLM that's accessed there. We have the application, we have data resources, we have orchestration. The model itself is quite late in the process. So the time it gets to that very first token being generated can actually be a significant amount of time, meaning, a few seconds perhaps. The point of that is that model, the large language model itself, is not the system. There's more to the system. So today we're going to look at some ways in which the models might be part of a system, and also different types of models that might be able to be more useful in particular contexts. So which large language model do we use? So the idea here, and this is even true for even ChatGPT, but particularly for even other systems, is for ChatGPT, sometimes OpenAI will allow us to select which model we use. We can use a small model or a big model. Certainly Gemini does this. They have their nano models, they have their larger models, their flash models. And the reason they have these different models is because you don't want to spend more resources than what the problem requires. So the idea of choosing the large language model is part of it is, and it does matter which model you use, because the way we do this is through abstraction. So the idea of abstraction is that we generalize which model we're going to use. So here's an example of abstraction. So the idea of abstraction is hiding details. So what is this a picture of? And I show this to my students. It's like, well, I don't know what that's a picture of. It's like just a bunch of paint on a canvas or something like that. Well, it's actually a picture of the United States of America. So if you look carefully, you can actually see the United States there. This is abstract art, meaning it kind of hides the details from the viewer to some degree. So for computer code, we hide what's being done, we hide how it works. All we know is we have to give it inputs and outputs. This is a key thing with using these types of systems is sometimes we need to know about all the details, but sometimes too much knowledge of the details is really not necessary here. We just need to know what the inputs and the outputs are going to be. An example of this is Grok, which surprisingly, since I created this slide, the company Grok was actually quasi-purchased by NVIDIA, not completely purchased by them, but in a tight licensing agreement. But with Grok, you can actually use different models. So here, there's a little menu here on the right side of the Grok user interface. And if you select that user interface, you can select at this time that I did this screenshot, you can select Llama 3 70B, Llama 3 8B, smaller model, Mistral, which is a mixture of experts model. You can select different models with different context windows. And that was the idea, is that you could pick different models. And so that's the idea of abstraction, is that we defer the decision of actually which model we're going to use. We might create a prompt, and then later we say, okay, which large language model will we use in our system for that? And that's a tremendously useful thing. I found it in the things that I develop, tools, the AI tools that I develop, that it's very helpful if I can allow it to be flexible and use different types of models for different purposes. And that's the idea of abstraction. Pick whichever model you want. So you're deferring that. How do we achieve abstraction? So here, this is actually another one. This is the GPT. This is, again, an old screenshot where you had GPT 3.5 and GPT 4. This is probably a screenshot from 2024. But again, picking different models. Oh, actually, it's from 2023. There we go. I forgot I had that. In OpenAI, they have a playground that lets you abstract even more. You can pick a lot of models and see how different models will behave. And so it's kind of like ChatGPT, but you have more control over the chats that you use. The way that we accomplish abstraction is through an API. So what is an API? It is an application program interface. So if we're going to call a large language model, we do it through an API. And I'm sorry to have to show you a little bit of Python computer code here, but here's a little bit of this. And I'm just going to explain briefly what it does. We load the model from a library. A library is a collection of different program elements that we might use. We link to the API. We get a prompt from a user. What question do you have? We call the API, and this is an old API here, completions. We've gotten away from that. OpenAI does not use completions anymore. As of this time of this video, they actually use one called responses, but completions was one that they used for quite a while. And you tell it what model it is you want to use, in that case, GPT 3.5. You pass it to the prompt. You pass the prompt and you give a system message, which will be a topic of a later chapter. And then you grab the response. So that's the way it works to actually interact with a large language model using Python. And ChatGPT or any type of user tool that we have is going to have something in the background like this going on that's going to process the prompt and feed it to an API so that the model can access it. Okay, then we display it to the user. Okay, we can access any available model. So for this API, this one we've selected GPT 3.5, but we could substitute and put any model in there that uses that same API. And we can even have access to other providers, such as, the Claude models, or the Gemini models, or other types of models by different producers from Anthropic or Google or whatever. We have here in this API the idea of a metaparameter. And in this case, it was the temperature metaparameter. That's a metaparameter we used in some of the prior models. There's other metaparameters today, such as, reasoning extent and other types of models. We have parameters indicating how many tokens we want to produce, max tokens, and things like that. So a metaparameter is just basically a parameter that controls how we want it to behave. We also have the message parameters themselves. We're passing them to the API in JSON. So I do want you to kind of see JSON, because we are going to use JSON in some of the tools that we use. It's basically a way to structure things so that the API will know what the data is we're giving it. So we have, in this case, a role. The role is user. The content is the prompt. The role is system, and so forth. So that's the JSON object. So look that up if you need more information about JSON. But it's just a simple way of structuring information. There's other ways to do it, YAML and others. There's other ways we can structure information. But in my experience, JSON tends to be the most popular. All right, so here's an AE chatbot like ChatGPT or maybe some other one. So this is kind of a flowchart diagram of this. So again, this is a simplification. This is a dramatic simplification. It's actually much more complex than this, but I'm just trying to simplify it so we don't get overwhelmed. So the user enters a prompt. So you type in your prompt, which is, what are great vacation spots in Idaho, or whatever it could be. Then it does some pre-processing. We talked about that in a prior chapter. We do things like tokenization, semantic embedding, positional encoding. So you should understand those from the prior chapter. Then we analyze the prompt, or the tool does. It analyzes the prompt. It says, okay, what kind of prompt is this? What are they asking for? We kind of pre-process it. Is it a toxic request? Are they asking us to do something that's outside of our terms and conditions and scope? Things such as, I don't know, things that might be harmful to others, like, ways of creating bombs or things like that, okay? So if it's toxic, then we just say, we can't do this particular thing you've asked me to do. Is it about image generation? Now, again, oversimplification, because we actually can accomplish this through other means that will be discussed in a later chapter. But in essence, the large language model that we might use to analyze this would say, okay, if this is about image generation, then we probably need to call an image generation model, and often they'll create a more explicit prompt. They'll create a prompt that has more details and about what the user wants to create. And then it calls an image generation tool, and that image generation tool will create the image that we can display. Okay, do we need current information about things that are happening since the training cutoff of the particular large language model? This is actually kind of standard these days, that it actually will go out and do some type of a search. It'll go search the web, we'll find some documents. I find that most of the chat models, ChatGPT, Gemini, whatever, they tend to just by default go out and call some search, and then use that information in context to build more accurate results. Do we need a calculation? Large language models are great for predicting tokens, but they are horrible for doing mathematical analysis. That's just the nature of how they are. If you ask what TWO plus THREE equals, it will tell you, I'm hoping, FIVE. But it does that semantically. Okay, it's not really great. Large language models are not really great at that. But Python and other programming languages are great at that. So if you need a calculation, what you'll often do is first generate some Python code, and then after you generate that code, you can call a Python runtime API. So you basically pass that Python code to a Python runtime, which basically runs the Python code and does the analysis and produces wonderful, mathematically correct, hopefully mathematically correct results. All right. If you don't need calculations, then you wouldn't have to generate that code. Then you add system and prior messages in the thread. So these chat tools all have lots of system instructions. You don't see them, but they go with your prompt. They tell it what to do, how to format the results, how psychopathic it should be, how, how it should format things, how much detail, stuff like that. It may access some storage. It may look at the thread, the conversation thread, and include that in the prompt. Usually they'll do that, which can be a good thing or bad thing. There's a separate issue that we'll talk about later. I'm expecting we'll talk about, can't remember when, but it's called context rot. So we haven't talked about context yet. That's later chapter 5. But the idea of context rot is that sometimes you can have too much information, and that thread storage can be a problem because you are accessing information that might not be relevant to the current prompt. Then you call the large language model using the selected model, again, abstracting so that we could, defer which model we're going to use. And then we filter the results, make sure there's no toxicity, other problems in the results. And finally, we might display that to the user. So I know it sounds kind of complicated, but trust me, it's a lot more complicated than this. But that's an example of an AI chatbot. All right, embeddings in vector databases. This was from chapter 2, so it's kind of a review, but I kind of feel the need to kind of go over some of this a little bit more because it's going to be relevant to what we're going to talk about next, which is RAG. So, way do we represent words as numbers? Again, from chapter 2, one-hot encoding. You don't really have to understand one-hot encoding, but it's just an alternative. With that, each word in the vocabulary has its own column. So again, large language models, they are mathematical models. They're made up of a whole bunch of perceptrons. And they need numbers as inputs. They provide numbers as outputs. So we could say, okay, if we let each field here represent a word, this could be the fourth one, is could be the third one, could be the first one, or whatever like that. Okay, that is nutso. That is going to be intractable because we just can't track what every word is. I mean, it actually, in theory, could work with very, very small vocabularies, but it's mostly zeros. So instead what we do is embedding. We change words into meaning. Fewer dimensions, maybe 512, although sometimes it could be 1,500 dimensions. It's basically, we turn it into what we call the vector. So this is a fake example. It's not a real example. Again, we're reviewing this from chapter 2. But here, understanding the embeddings, the first embedding there is man, and it has actually 7 dimensions here, 7 numbers. This is not how, unfortunately, how embeddings in real life are represented, because we don't actually know what the numbers mean in real life. They're just trained based on some massive corpus. But imagine that we hand-coded some, and we said, a living being, man was a 0.6, so it's mostly a living being there, if we consider on a scale from +1 to -1. It is -0.2, it is not a cat. It is a human, it has the gender, that's actually an incorrect statement there. Instead of gender, I think I pointed this out in chapter 2, it really means maleness here is the gender. So here we're having maleness be positive and femaleness be more negative numbers for this particular one. And I got this from some internet. Somebody else created this thing. The source is in the footnote here, but you can't see that. It's from a blog called arise.com. So that's where I got this from. Royalty, not, verb, and things like that. To the right is a little diagram showing in 2 dimensions, which again, this is 7 dimensions. It's hard to view things in 7 dimensions, but in 2 dimensions, there's the man would be represented there. There's another one that is woman, which is very similar in numbers to man. Woman is a little bit more cat-like. I don't know exactly what that means. The gender is negative, meaning it's not high in the maleness dimension there. Other ones are kind of similar there. Again, these dimensions, the embedding dimensions and the values, are usually learned from large corpuses, so they're not exact, but they're kind of approximated based on the training set. Here we have king and queen, and again, king and queen are similar. The big difference between king and queen and man and woman is that king and queen have royalty as a higher value. And they also have the genders as kind of representing, king is more maleness than the queen is. The idea in the picture at the right is that the relationship between man and woman is similar to the relationship between king and queen if we were to view it in 2-dimensional space. All right, it's kind of confusing, I'm sorry, but I think my explanation in class is probably clearer than that. There's this semantic galaxy. That thing it's actually interesting to look at. Interesting tool, but it's kind of cumbersome, so I'm not going to demonstrate that right now. There is this idea of coming up with embeddings that we've talked about. Again, reviewing from chapter 2. There's a tool here, Wevy, and what it does is it lets you view in a couple of dimensions, view embeddings here. And there's the website here. So let me just switch to that for just a second here and show you Wevy. Hold on just a second. I had this loaded here. Where is it? Wevy, where are you? Oh, here we are. Here's Wevy. So what happens is we have this network with apple, drink, eat, juice, milk, orange, rice, and water. And then one hidden layer. A single hidden layer is usually trouble. Actually, let me give it 2 hidden layers here so that it can, is it learning right? I can't remember how to change this in the configuration. There's a way to change the number of hidden layers, I think. Oh, maybe it only has 1 hidden layer. Oh well. Anyway, what we're trying to do is find the connections between fruits and juices and things like that. And then we have a data set here. The data set, this is a goofy data set, but we have kind of you eat an apple, you eat an orange, you eat rice, you drink juice, you drink milk, you drink water. So it's kind of what you learn from this. This is not how a real corpus looks like. And then what I can do is I can actually come in to this thing and I can start it. And let me run it for some iterations. I'll run it for 100 iterations here. So what it does is it takes the data from the training set and it feeds it into the model. And I don't know if you saw that, but when it did this, at the bottom we have the weight matrices where, I don't remember, let's see, blue is positive and red is negative or something like that. So it does it based on the vectors, and then in the right we have in 2-dimension space, it tries to represent these vectors. And what happens is we do the training. Let me just clear this again so you can watch the lower right-hand corner. Okay, I'm going to restart it. Everything's kind of random, and I'm going to go for some 500 iterations. Things kind of move in the space, this vector space, that we see that the word drink and milk and water, they kind of go together, and rice and milk kind of go together because there's rice milk. This was in our data set, I believe. Yeah, rice and milk was in the data set. Water and juice. Anyway, it kind of learns the patterns and kind of groups things. I don't know if this was helpful or not, but anyway, it's just this idea is that we have the hidden layers to do feature detection and find out how things kind of go together. We just feed into the data, in this case 500 times, and result those 500 iterations of the training, feeding the data in, and we kind of learn the model. All right, let's go back. I think I'm going to probably avoid showing some of these tools because they can be a little bit unnerving. Okay, word adjacency. Basically, you have some words, you're trying to find words that are missing, skip grams. I'm going to skip this stuff here. I just want you to understand embeddings. I want you to understand that we have a list of numbers, and that list of numbers indicates the meaning behind the token, which the token is part of a word. This is another tool. I was going to show you this, but I'm not going to now. It's another one. It's on GitHub. And what it does, it shows you can do analogies between king and queen and aunt and uncle, nephew and niece. Again, the idea is that in the semantic space, which means as we position these things, we see on this particular one, we have at the bottom a woman and the top a queen. And then what we see is that kings are more queen-like than men are. And we see that brothers are more he-like than sisters and things like that. So it's just showing that dimensions. But anyway, I don't know if that's helpful or not. But just understand embeddings. Embeddings are absolutely essential to comprehend. When we do inference, again, from way back from chapter 2, we provide our input, we pre-process it, we give our prompt, we give it some context. Okay, context is important because without context, the prompt it's just using its training data might or might not be tied to what we want. So we have to think about what context we give it. It could be a document, it could be data. Okay, it goes through the hidden layer, it goes through the model. Again, in transform architecture, this is a dramatic oversimplification. We still have attention mechanisms, and we have feed-forward networks, and we have reduction layers and different things like that. Softmax, other things that I'm not even going to take you through. So trust me, Dramatic simplification here. I just want you to understand as it goes through the network, we are looking for patterns. We're looking for features that then would indicate how a particular input might lead to a particular output. With the output, we then unembed, we detokenize, and eventually we get words back. And that's your response. And that happens in seconds. You know, it's a wonderful thing that can happen so fast, thanks to the transformer architecture and parallelism. All right, what if we have a lot of context? What if our context is, you know, hundreds of thousands of tokens? You know, it's a book or multiple books or documents, and it's just very extensive. And that could be a problem. We could feed that all in, but alas, we have token limits sometimes, you know. The context window. This is chapter 5. I'm sorry, getting a little ahead of myself here, but there are limits to how many tokens you can feed into a large language model at one time. And perhaps even more relevant is these things can cost money. You pay per input token. There's a cost per million input tokens, and trust me, you can burn through that pretty darn fast if you have a lot of context. Context is good, but it can be costly. So what do? We use RAG, which is what we're going to cover today in chapter 3. So RAG is retrieval augmented generation. It is a great thing. What you do is you take that big context and you pre-process it. You tokenize it and you embed it. Just in one big pass. And then what do you do with those embeddings? Okay, that could take you a little while to do that. I mean, it could literally take you, 10 seconds or a minute or more. Depends on how big your context is, even on fast processors. You put it in a vector database. The vector database is basically a bunch of vectors, a bunch of embeddings that we store chunk by chunk. So we take this entire book and we break it down into little chunks, like maybe a page at a time. They're not really a page at a time, but little chunks, and we embed each of those chunks and summarize the embeddings, and we put it in a vector database. And then what we do is we create an index. We keep track of what's in the vector database, and we index it according to embeddings, which are summaries of what each chunk represents. So this chunk represents things about snow skiing. This other one has chunks about mountain biking. Let's imagine the context that we're providing here. This resource is about different sports. So there's one about snow skiing, there's one about water skiing, one about mountain biking, one about the best one, the most important one is about pickleball. So we have all these different sports in this database. And then when we get ready that we want to do our inference, what we do is we give our prompt. My prompt is, what's the best technique for third shot drops in pickleball? So that's my prompt. We then determine the embedding of this, and we find out it's about third shot drops, it's about pickleball. And then we do a semantic search. Okay? So we look in the database for chunks that have to do with third shot drops and about pickleball or whatever we're talking about in our prompt. And we retrieve those chunks and that are pre-processed. They are included with the document query as the context. So not the entire database, not the entire book, but just those pages. You see how this pages. So you think about this like a book. If you have a book that you use as a reference book, it could be a big long book. But if there's an index, you just look up those pieces that you want and use those in your study. So then we run it through the network, through the large language model, and we process it and we get our answer and we're happy. Because the answer actually has the chunks, has that relevant information from our large context that's included in creating the answer. That, my friends, is retrieval augmented generation, or as we affectionately call it, RAG. RAG gives prompts context, or we give the context, but it gives any individual prompt, it gives them the context. So, I will say this about RAG. RAG has become very popular. It really kind of took off it started really in 2024, really took off in 2025. I think we're to the point now in 2025, I'm video recording this in 2026, but in 2025, where really RAG has become almost a standard for tool builders and things like that, just because it can improve results so much. All right, RAG, creating custom bots. How do we do this? So what we do, this is a simplified RAG system. On the left, we have the user. They provide their prompt. oops, I'm sorry. We do the, I thought I had some animation here, but I don't. You then do the search. Then you find your data sources. You can have structured or unstructured data that you're retrieving. Then you can retrieve that. You add the context to the prompt, call your large language model, then goes back in the user interface back to the user. So sorry this isn't animated. It's something I got from that particular Hatchworks source below, but I think it's a wonderful simplification of how RAG works. In a nutshell, what is RAG doing? It's letting you specify what data sources, what context you want to use to answer your questions. So you're not relying on the large language model's original training data, which could be accurate or maybe not accurate, maybe not up to date. You have a homework assignment. This year, in 2026, I'm giving this as an assignment after covering Chapter 3. Or no, are you doing it before? No, actually, you may be doing it before. I don't remember. Anyway, you've either done this assignment or you will do it in preparation for the next class session. You too can do RAG. There's all kinds of these out there. Chat with PDF is one that I've enjoyed using. Very easy to use. Just drag and drop. It's very easy. They have a pretty reasonable free tier up to, I think, 10 megabits of data, but it's a great one. PDF AI, ask your PDF. Some of these may be out of business by the time you watch this video. Lots of agent builders out there. Pretty much everybody that has agent builders these days, they'll do RAG. RAG has become such a standard that everybody does it. All right, let's move on. So that was RAG. Mixture of experts, okay? So this is not necessarily about the entire system, but about AI models themselves, about how we design them and kind of have a system within a large language model. All right, so this diagram kind of represents, and I'm sorry it's kind of inverted. I don't know. I do know why they put the input at the bottom, is that for some reason in these models that represent, these diagrams that represent AI models, for some reason they have the input coming in from the bottom instead of from the top. Kind of weird. But with this, you have the input, and it goes into a gating network. And the gating network basically takes the input and says, what kind of input prompt is this? What are they asking for? Are they asking for things about sports? Are they asking for things about history? Are they asking for things about, literature? What is it? And then the large language model has a bunch of expert submodels that each specialize. One of them might specialize in questions about sports. Another one might specialize in questions about history. And what the gating network does, it says, which of the models should we use? So it takes a large language model that potentially could have trillions of parameters, very complex model, and each of the submodels may only have hundreds of billions of parameters, much smaller. So it's much more efficient. Instead of having that prompt go through every one of the models, it just only goes through the models that are relevant to the prompt. So if I ask a prompt about, hey, tell me the history of pickleball, it might pick the sports model, which could be expert 1, and the history model, which is expert 3. And it doesn't even pass it through the literature model because that's not relevant to this one. So what it does is it then passes it through the models to predict what the ultimate token that you generate is. And then the gating network, which is kind of the boss here, it would then weight the outputs of the experts based on which is most relevant. Okay? So in a nutshell, what we have multiple large language models within our model here. So submodels, each is trained on specific tasks. The gating network determines which expert to use. They also call this expert choice routing or switch transformers. You don't need to know those terms there. In my course, in the chapters, you have the bolded terms that are listed and summarized at the bottom. Those are the terms I really want you to understand. The output is a weighted sum, as I just mentioned. Here's a few examples of ones as of this video right now. Some examples of mixture of expert models: GPT-5, Gemini, Minstrel, 8x7. The 8x7 for the Minstrel model, I believe, means, I can't remember which, I think it means there's 8 billion parameters and there's 7 experts. Or it could be the other way around. But anyway, my suspicion is all of the large AI models, the foundation models like GPT-5 and Gemini, and I realize GPT-5 today is not even the most current. I think GPT-5.2 is the most current as of this video thing. But anyway, that's a mixture of expert models. All right. Oh my goodness, I have a meeting coming up here, so I gotta wrap this up here. Thank you for enduring thus far. You're probably watching this at double speed, so you're doing okay. Another topic is agentic AI. So this is kind of a big thing going on. 2025, agentic AI kind of took off and it became kind of the standard here. So we have this idea of workflows and data pipelines. A workflow, here's a simple example I found on the internet from some free show, something or whatever. It's collecting permissions from parents. It's basically multi-step. So you need to get permissions for an upcoming field trip at the elementary school. You fill out a template, email it to the parents sign it, they email it to the administration and store it in a database. That's a workflow. It's just a bunch of steps that you use to accomplish a task. We also have data pipelines. It's the idea that we collect some data, we ingest it, we prepare the data, we do computations, and we present the data. So it's just, think of a data pipeline as a workflow acting on data, processing data. Okay, just a bunch of steps that we do. So that's really what the agentic AI is really about, processing workflows with a bunch of steps. We call these agentic workflows. It's kind of a buzz term, but it's becoming more common these days. So let me give an example. This was from my homework assignment that my students would have done, but maybe you're not doing in some other course. A Zapier Zap. So here we have the Zap that we did for our homework. It was very simple on the left. We have a new email message comes in, and we summarize that and store it in a Google Sheet. That was the homework assignment for our Zapier agent. If you do this, you do that. So if you get an email, you get an email message, do that, store a summary of it in the spreadsheet. Here's another example, a diagram that I found online using Zapier. A contact form is filled out on Facebook. When that comes in, then you send an email thanking them for signing up and contacting. But then you also need to contact the people that will respond to this contact us inquiry. So there's a chat channel that sends it to Slack, a Slack thing where we have somebody who will process that thing or whatever like that. So it's kind of multiple steps. So that's kind of the idea here. I tried to pick some super simple examples that are not overly convoluted here, but anyway. There's an issue related to this, which is if we're going to use agents, we have to give access. So, for example, that Zapier one, we had to give Zapier access to our Gmail account if we wanted it to process our incoming email. So, agentic workflow, there's security issues we have to deal with. And I have a separate class discussion we may do at some point later in the course, controlling or revoking access to your Google account. When you use Zapier and a lot of these tools, you have to give access to data or they don't work. They need to access data. If you have data is in your account, you need to give access for it to work or it's not going to work. It's just how it is. Make sure you trust the app. Only grant as much access as needed. This is kind of some rules of thumb here. Okay, so sometimes some apps that I've seen, you need it to access your Gmail. It'll say, can I access everything about your Google account? And I say, no, you can't. You can only access my Gmail. Be prepared to revoke access if necessary. So you can go into your settings of your Google account and you can revoke that access and delete the access so that Zapier can no longer access that. So it's just kind of an idea of how these things with agentic workflow. That is a big debate that's going on these days with agentic workflow. People say in the future, the AI models are going to go out and plan our vacations for us and book reservations at hotels and book our flights and things like that. Sure, that's true. But I don't know if that's such a good idea if we do it completely unguided by the humans. The idea of human in the loop. I don't remember if that was in chapter 3 or not, but that's essential is where do the humans come in and say, no, I'm not going to give you access to this. I'm not going to give you my credit card number or whatever like that. All right, new topic, multimodal models. There is an entire chapter devoted to this. I'm going to do this very briefly here. Generative AI models, they can take lots of inputs. And large language models, they have text as an input, but we could also have inputs like images as inputs, audio as inputs, video, whatever. Actually, on my watch, it will do my heartbeat. It actually keeps track of that. So I could have AI running on my watch that is using AI as an input into some kind of a model to try to predict my health condition or whatever like that. So we can have text to image. It's funny that I'm in this slide, I'm mentioning DALL-E 3 and Stable Diffusion. These are old models that we don't even use anymore. Anyway, there's newer models, Nano Banana and stuff like that from Gemini. Text to music, Suno. Suno 3. That's so funny. I just used Suno this past week, and it was Suno 5. So Suno 3 was their old version. Udio is another one. They may be out of business by now. Text to audio, 11 Labs was kind of a leader, pioneer in this. A big lead, early, I should say early pioneer, because there's companies well before 11 Labs, but they were one that did text to audio. So speech models, it's a popular thing. To video, Sora. Oh my goodness, this is an old slide from probably 2024. Pre-release, Sora was available. I had some Sora examples. I won't drag you through them now. Sora is no longer really, I think, state-of-the-art now. There's other things better than Sora that will take text, you prompt it, and it will create videos for that. Covered in a later chapter, chapter 10, I believe. Here's my Sora example. This was probably, again, from 2024. This was supposedly really cool and mind-blowing in 2024, where...
Thank you for choosing Stubbs Dental Implants.
Sorry, why does it give me an ad?
Let's get started on your...
Sorry.
It is a beautiful drone shot.
This is where they were talking about Sora-generated video. Back in 2024, this was kind of mind-blowing. These days, it's just kind of commonplace here. All right, forget that. Let's move on to something more interesting. Okay, it was Sora. Oh yeah, I had this Sora thing. I may show this in class. Cosmo, the cougar, comes from an egg. The first one actually was kind of stupid. The second one came out better. Actually, maybe I'll show you that one. Let's see if this shows up here. Although I gotta hurry because I have a meeting coming up here. But here's what Sora generated for me. I gave it the prompt: an egg in a nest hatches out, and out comes Cosmo the cougar. So here's the video here, the BYU Cougar mascot. So there's an egg, and there is Cosmo. So okay, that wasn't so bad. All right. I know that seems kind of like simplistic by today's terms, but that's what we had in 2024. Maybe that was early 2025. But okay, reasoning models. This is a supplement to the chapter. They took off in 2025. Before that, we really didn't have reasoning models, but then this kind of became the thing here, reasoning models. So we have non-reasoning and reasoning models. Non-reasoning models, pattern recognition. They do token prediction. We already talked about this in chapter 2. We have an input, we have an output, okay? We already talked about that. We might pause to do tool calls, RAG, SERP, search engine results page, where we're actually looking at the internet, code execution. We talked about that at the beginning of this video here. Reasoning models do the same thing, but they are embedded in a reasoning workflow. So it doesn't just call the model, even within the system, or even just with the pre-processing I showed you at the beginning. What it does is there's a workflow surrounding the call to the large language model, including asking, what is being asked in the prompt? What is the person really asking us here? So it will actually iterate on that. It'll first say, what is this person asking in this prompt? And then a large language model will say, what should the answer look like? What are we looking for? Is it going to be an image? Is it going to be, a data table? What are we looking for in the answer? What will be needed? What resources will we need in order to provide the answer? What are the steps that we need to do? And it'll come up with a list of steps that you need to do. This is before we even generate the actual answer to the prompt that the user gave us. Then we execute the steps. Very often they hide the tokens until they get to the answer. In some cases, you can actually click on a little button and it will tell you all the gory details of all the reasoning. What is being asked? What does the answer look like? And things like that. But sometimes if we don't, it'll just jump us to the answer. When it actually gets to an answer, it doesn't even give us the answer yet. First, it might verify it. And did we get the answer? If yes, then give the user the answer. If no, it'll go back and do it again. I've actually had this where you ask a large language model, reasoning model, a question that it really doesn't know the answer to. And it would just crank at it and say, I'm trying to get the answer. And it just keeps cranking at it, burning through tokens, until it either gives up and it gets some stopping condition or it gets some semblance of an answer that it might fabricate or something like that. So, all right, so reasoning gives much better answer, but at a cost. And this is something to recognize, is the reasoning models. Sometimes they're bigger models, sometimes even not bigger models, but still, the fact that they are spending all this time reasoning, there's a cost to that. It's, you know, in terms of token use, it's slower as well. So we have to think about reasoning. Too much reasoning can be a bad thing. You're just wasting tokens and wasting computing power and wasting time as well. So something we have to manage is type of reasoning. A comparison here, I have a meeting coming up, so I gotta kind of shortchange this here. They have different functions, there's different processes, they're best for different purposes, they have different strengths, they have different weaknesses, they have different underlying mechanisms, they have different analogies. This is something I got from a GPT 2.5 Pro prompt about this, but it makes a lot of sense here. Pause the video and read through this if you want more details about this, but it's probably more information that you really want to know about this difference here. But the key is understanding that there are differences and that one is not necessarily universally better than the other. All right, last but not least, hybrid models. This is pretty basic here. We're seeing a lot more of these show up these days. So we have, basically, I created this. This is my own little flow chart here. Sorry, a little too simplistic and not the best model, but we pre-process the prompt. Does it require reasoning? If yes, reason. If no, don't reason. Actually, the reality is it's not does it require reasoning, it's how much reasoning does it require is what we ask. And if it requires a lot of reasoning, we scale up the reasoning. If not, we do less reasoning. Reason when needed, as much as needed. If there's no reason, we don't reason with that. Okay? The one last thing I included in this chapter, and this had to do with the introduction of reasoning models in 2025, is that sometimes the old models, in fact, it was GPT-4 and 4.0 had some problems. When GPT-5 came out, what happened is that it tried to address an issue that we had with GPT-4, and it kind of overcompensated. That issue is psychophancy. So I kind of tacked this onto this chapter. I probably should cover this issue in another chapter, like the chapter on prompt engineering or something. But what is psychophancy? Interestingly, I'm surprised that my students haven't really heard about it thus far, but it will be something that we have to deal with large language models as well as, you know, people that we talk to, you know. It's excessive agreeableness. It's the idea that the model is trying to agree with us even if we have bad ideas. And it's unfortunate that this has happened, and part of it comes from the way that the models are fine-tuned, that they're fine-tuned to be agreeable. It's kind of buttering us up, you know, meaning you give the model a bad idea and you say, what do you think about this idea? Say, oh, that's a great idea. And it's due to the training, and it's due to how we fine-tune these models, reinforcement learning by human feedback. The fact is people like to be agreed with. And so when they fine-tune these models, there's tend to be a propensity or a bias towards agreeableness. Telling people what they want to hear. So here's a Dilbert cartoon. That's my plan. What does everybody think? And then this guy over here, this employee says, oh, that's brilliant. That's the best plan you ever made. Woohoo! And then the boss guy says, that's the type of honest feedback we need. And then the employee says, I love it when you exhale in my direction. Anyway, okay. Kind of silly cartoon, but it's just this idea. Sometimes psychophancy can be a real detriment because it biases the model towards agreeableness, and not just giving us honest answers, or I shouldn't say honest, but truthful answers. But these models have a hard time knowing the difference between truth and error. That's a discussion for a later chapter. But but we've actually found, though, when GPT-5 came out, they actually had psychophancy filters in it, and it was not agreeable, and people didn't like that. So now they've allowed us to kind of scale the psychophancy a little bit. It's, you know, you want a little bit of agreeableness, but not excessive agreeableness here. So anyway, that's all we have for chapter 3 as this, you know, incarnation of the chapter here. And I don't know if this was helpful or not, but the intent is to provide you a little bit of review of chapter 3 concepts, a little bit more detail if you want that. Or you can just study the chapter and use your large language model or the AI tutor to help you kind of explore concepts that you need more explanation of. And that's all for today. Bye.